So these are the example of our doubly reinforced concrete beams. So we have a rectangular concrete beam having a width of 250 millimeters and an effective depth of 400 millimeters. It is to carry a factored moment of 272 kilonewton meter. The compression reinforcement, if it is necessary, is placed at a depth of 60 millimeters from the outermost compression of concrete. We are asked to use Fy equal to 344.7 megapascals and F prime of C equals to 20.7 megapascals. So now we are asked to determine what is the required tension still area. Okay, so for example, this is our beam. It says that we have a base which is equal to 250 millimeters and our depth the is effective depth that is from AS to the topmost fiber of compression. We are considering the midspan since it is not stated whether it is a simple beam or what type of beam. So this is our D, which is equal to 400 millimeters. Now, if ever that compression reinforcement is necessary, it is placed at the depth of D prime, which is equal to 60 millimeters. Okay, so first one is to check whether compression reinforcement is really necessary or to check whether the beam is really a doubly reinforced beam or not. So in order for us to check, so first step is checking. For us to check, it must be that your actual MU is greater to the maximum moment capacity of the beam if it is a singly reinforced beam. So to solve for your maximum moment, it is equal to your reduction factor F prime of C times your omega multiplied to your base times your square of your depth multiplied to 1 minus 0.59 omega, wherein our omega is equal to your rho max multiplied to your Fy over F prime of C, wherein our rho max is given as the formula of 75% of our raw balance, wherein your raw balance is equal to your 0.85 of your 75% of your 0.85 F prime of C beta 1 all over your Fy times 600 over 600 plus Fy. So that is your maximum raw. Okay. So for your maximum, raw maximum, this would be equal to 75% of 0.85. Our F prime of C, which is given as 20.7. Your beta 1, since this is less than 31, your beta 1 is 0.85. And your Fy is 344.7 multiplied to 600 over 600 plus 344.7. The result of this would be 0.75 times 0.85 when your beta is 0.85. Our raw maximum is equal to 0.20 0.02067. Okay, so now we can solve for our omega. Our omega is 0.02067. Fy is 344.7 over 20.7 of f prime of c, and it would give us omega as 0.3442. Now we can solve your mu. That is 0.9. F prime of c is 20.7. Your omega is 0.3442. Your base is 250. The depth is 400 squared. Multiply to your 1 minus 0.59 of omega, which is 0.3442. And your maximum mu, this is maximum, would be equal to 204.409 kilonewton meter. So this is less than your mu, which is equal to 272. Therefore, our beam is a doubly reinforced beam. Since this is a doubly reinforced beam, we are now ready to solve for our reinforcement. So we will solve. Since this is a doubly reinforced beam, your AS is equal to AS1 plus AS2, wherein your AS1 is equal to your maximum rho multiplied to your base times depth. So your AS1 is equal to your maximum rho, which is 0.02067. Your base is 250 and your depth is 400. Your AS1 is equal to 2,067 square millimeters. Now, for us to solve for your AS2, this is your AS2, we will solve as by solving your A. Okay, so to solve for A, we will solve for A that your A, so we assume that your first tension is equal to your first compression. This is AS1 Fy, which is equal to 0.85 F prime of C A of B. Then this is your 2067 multiplied to your Fy of 344.7 equal to 0.85. Your F prime of C is 20.7. A is unknown and your B is 250. This would give us A equal to 0.02067 This would give us 161.977 millimeters. And it would give us the value of C, wherein C is A over beta. That is 190.561 millimeters. Okay, so we have to solve whether your steel in both tension and compression is yielding. For tension, the formula would be 600 multiplied to D minus C over C, wherein 600 multiplied to D, what is your D? That is 400 minus C of 190.561 all over C of 190.561. This is Fs, 400 minus 190.561 over 190.561 multiplied to 600. This would equal to 659.439 megapascals, but this is greater than your Fy, therefore tension yields. How about our compression? For compression, that would be equal to your (600) multiplied to your C minus your D prime all over your C, wherein this is equal to 600. Your C is 190.561 less your depth of 60 over 190.561. This would give us 411.084. This is also greater than your Fy, therefore compression also yields. Okay, since we already know that the reinforcements in both tension and compression is yielding, we are now ready to solve our number or the area of our reinforcement. So we will have a two diagram. The first one is like a singly reinforced diagram that we have your compression block, which is the width of the compression block is 0.85 F prime of C and its depth is B. So this would be multiplied by to B. Then the height is A of our compression block. Of course, our compression is acting at the centroid. So this is A over 2 from the compression fiber, and that is equilibrium to T1. So we also have T2, which is from the uppermost fiber is equal to D prime. So in order for us to have your AS2 and AS prime, so since our steel is yielding, our AS prime is equal to AS2. So we can use either of the two formula. We can use your formula for tension, and we can also use our formula for compression. But in this problem, let us assume that your formula for tension. Therefore, your MU would be equal to your phi multiplied to your AS1 Fy. Your lever your moment arm is equal to your D minus A over 2 plus A is 2. Since it is yielding, we are also using Fy multiplied to D minus your D prime. Okay. So your moment is 272 times 10 raised to 6. Your phi is 0.9. Your AS1 is 2067. Fy is 344.7. Your D is equal to 400, I think. 400. Your A, what is the value of A? A is 161. Okay. A is 161. Is A 161.977. 977 over 2. This is divided by 2 plus AS2, which is unknown to us. Our Fy is 344.7 also. Your D is 400. Your D prime is 60. So our AS2 is equal to AS2 is equal to 639.330 square millimeters. So the question for us is to determine the required tension steel area. So that is your AS, which is equal to AS1 plus AS2, wherein your AS1 is 2067 plus 639.330. Therefore, your AS is equal to 2,706.33 square millimeter. So this is your tension steel area. Okay. If you are asked how many, so we will just divide this by the single area of one diameter. You can also determine how many number of compression bar by using this one, because this is also equal to your AS prime. Okay.